Hello, everybody. We are Team MEO1. I'm Richard Ira,
I'm Kara Connors.
I'm Ashley Sandara.
and we'll be presenting our project on the design and manufacture of an efficient and cost-effective swing gauge. Our faculty advisor is Tom Mealy, and our industry advisor is Pete Donaker from Aerocision, a customer-driven manufacturing company for aerospace OEMs. First, a brief agenda of our presentation. We'll talk about the project description and goals, then we'll talk about the design approach and prototyping methodology, and we'll go through our final design and then finish off with a summary and recommendations.
So our project is to design, test, and build an inner and outer diameter swing gauge. And Aerocision has given us a list of set criteria that they'd like us to meet throughout this project. The first being is that the swing gauge has to be able to read a diameter range between 2 and 20 inches, as well as cost $300 to $400, which is currently 1/4 to 1/3 of the current swing gauge that Aerocision is using right now. And the swing gauge also has to be able to read up to 1/10,000th of an inch, as well as withstand temperatures between 68 and 72 degrees Fahrenheit, which is just a comfortable work environment on the Aerocision shop floor. And the calibration time for the swing gauge also has to be reduced down to 1 to 2 minutes. And some hard deliverables that we have to provide in this project are a SolidWorks model of the final design, as well as a critical design review presentation that we performed earlier in March. And we also have to provide a bill of materials and a cost breakdown of our final gauge. And we did do some prototyping before we got to our final design, and this in total is 3. Each prototype we wanted to focus on one specific concept to really focus on and improve. And as you can see in this video, this is our 3rd and final prototype that we did before our final design. And we are just measuring a circular part, and you can see that dial indicators just pick up any variance in that diameter reading.
Based on what we learned from prototyping, as well as our discussions with the Aerocision engineering team, we came up with the final design shown below, which includes 5 subassemblies that allow us to meet all of the project goals, including being adjustable between 2 to 20 inches and having an accuracy of 1/10 of a thou of an inch. We kept the weight of the overall gauge in mind with our material choice of aluminum 6061, as well as the usability for operators by standardizing all of the hardware.
So our gauge has to be able to hold gauge feet at a specific height. So our approach to this was to model a clamp similar to a bench vise. And as you can see, we have 2 different ones. The ones on the left is the one that's actually interacting with the dial indicator. So this is the one that's going to be picking up on the readings of any variance in the diameter reading. And the one on the right is the one that's going to be working with the axial base clamp. So this is the one that's going to be adjusted to the specific diameter that you would like to set it to.
The next subassembly is the dial indicator mount. We chose a compression/tension spring, depending on either ID or OD measurements, that works with the dial indicator and interacts with the gauge feet clamps Ashley talked about previously. It features a clamp style base for a secure, unmoving fit and a linear constraining rod to keep a consistent spring force.
The carbide base subassembly uses the same clamping style as the gauge feet clamp, and it provides a secure surface to set the gauge on while measuring a components that will not mar the surface of the component.
An accurate temperature and load simulation was important to ensure the measurements stayed within the accuracy range. For this simulation, we used a fixed support as well as the force of the spring and a temperature set the temperature to room temperature between 68 and 72 degrees Fahrenheit to see if the max deformation was less than 1/10 of a thou, to ensure that the base stayed within the accuracy range.
Shown now is the bill of materials, which includes all of the raw materials, purchase components, and hardware needed to make each gauge. The costs included are only reoccurring costs should they choose to manufacture more than one gauge. And as you can see, we are $10 under the $300 to $400 budget, which leaves some room to include the machining costs, because every manufacturing company has a different cost that they associate with hours of machining.
So in order to test the accuracy of our gauge, we wanted to perform a test that they actually do at Aerocision called gauge repeatability and reproducibility. And this essentially has different people measure 5 different parts and to measure the variance between all the readings to see how accurate your gauge is working.
So in summary, we'll be providing Aerocision with final assembly and manufacturing instructions so they can manufacture the gauge and perform gauge R&R testing on it. Overall, we really enjoyed working on this project and want to thank you for listening to our presentation.